So let's get started with this. Okay. So I'm going to share the problem that we're currently working with on screen. And you need to follow along with me here. So this is the problem. This is the problem that we're currently dealing with. Right? So I've deduced 3 simple steps that you can follow. These are the big picture steps that you need to take to solve any problem relating to time complexity, right? So first, you need to evaluate what happens for each value of I. So I is assumed to be your outermost loop, right? And then by this, I mean, you ask yourself, for each value of I, how many times does the inner function run, or does the inner loop run, right? And then step 2 is after you've evaluated for, let's say, I is equals to 1, I is equals to 2, I is equals to 3, I is equals to 4, you then sum up the terms, right? After summing up the terms, you're going to see a pattern. Usually you're going to see some sort of series, either geometric series or arithmetic series. But you need to figure out what's the pattern, right? What's the series that you're getting there? After getting the series, you need to simplify the sum, and then you'll eventually stumble upon your time complexity. So looking at this problem that I'm sharing with you on screen, I'm going to put it somewhere here. I'm going to put it over there. Looking at this problem, we see that if we start our analysis, we can draw a little table. So let's draw out a little table. We're going to have this. We're going to initially say, hey, this is where I'm going to keep track of the value I, right? And here, this is where I'm going to keep track of how many times does the inner function run. So I can call this inner loop, right? So in our case, we have outer. So I belongs to our outer loop, and then we have our inner loop. And then this is where we do our analysis, right? So looking at this problem, the first value of I, we see that it starts at 1, right? Then we ask ourselves, what happens when the value of I is 1? So if we look at our inner loop, you can see that we have j is equals to 1, j less than or equals to I, and then we have j plus plus. So when I is equals to 1, this inner loop is going to run 1 time. And then what happens to the value of I in the next iteration? We see there that it says I times equals to 2. So every time we have I times 2. I is equals to I times 2. On every iteration, you should keep that in mind. So the next value of I is 2. How many times does the inner loop run? Well, we see here, twice. Because it's going to run for I is equals to 1 and I is equals to 2. And then we're done. Right? And then we see I is now going to be 4. Right? I is now the value of 4. What happens when I is equals to 4? What's going to happen? Our inner loop is going to run 4 times. Right? And then we go to the very end. What's going to be the termination condition based on our for loop? So you have this thing, I less than or equals to n. So this thing terminates when I is greater than n, or when I is equals to n, we terminate, right? So this is you reading it from your for loop, this thing. So you have n, the last value, the absolute last value will be n. What's going to be the absolute last value? We can generalize this and say we're going to go up to 2 to the power of k. Why am I saying 2 to the power of k? See the pattern here. 1 is the same thing as 2 to the power of 0. 2 is the same thing as 2 to the power of 1. 4 is the same thing as 2 to the power of 2, right? And then the last item is going to be 2 to the power of some integer. which we choose as k, right? So we have this simple structure going on. Now, this, the sum of all of these terms leading up to the last one, that's going to give us the time complexity. So if we write our expression over here, we can say T of n is equals to 2 to the naught plus 2 to the first plus 2 squared plus up until 2 to the power of k, right? Obviously, you can see that this is a geometric series. And the formula for a geometric series, I'll put it over there. Let's put it over there. The formula for a geometric series is this one. So when substituting in the geometric series formula, we have 2 to the power of k plus 1 minus 1 over 2 minus 1. This is our T of n. So this is our function, right? This is our time function, right? Now, we have a problem. We don't know what the value of k is. We don't know what the value of k is. So how do we work out the value of k? Well, let's do a little observation. When I is equals to 1, we can see that the inner loop runs once when I is equals to 1, right? Perfectly fine. When I is equals to 2, you can see that the inner loop runs twice, right? When I is equals to 4, we can see that the inner loop runs 4 times. Now what happens when I is equals to n at our largest value? So the largest value of I is n, based on our termination condition, right? And I'll talk about why n is an upper bound in a second, but don't get stressed about this. You're gonna look at your for loop and look at when it terminates, right? And then you pick the upper bound. So it's gonna terminate when I is less than the last value, where I is less than n. It's gonna terminate. But we're gonna take the upper bound. We're gonna take I is equals to n, right? So what happens is we have this being equals to this. So this is the value of I, the last value of I, the biggest value of I will be n. And then this is however many times the inner loop will run when I is equals to n, right? So we have this expression saying n is equals to 2 to the power of k, right? You follow with me? Now we need to get the value of k. How do we do that? Well, here comes our logs, and they save our arsenal. The Arsenal team was gonna lose, but yeah. Let's go back here. So we're gonna take log of both sides. Log of n is equals to log of 2 to the power of k, right? And using log rules, we can bring k to the front and say k log of 2 is equals to log of n, right? And it's important for you to go back to your logarithmic rules, right? So how do you get the value of k? How do you make k the subject of a formula? We can say k is equals to log n divided by log 2, which is simply log 2n. We have k is equals to log 2n. Now we have the value of k. We're going to substitute this value of k in our summation formula. Let's go. So we have 2 to the power of log 2n plus 1 minus 1, right? Over 2 minus 1 is 1, so I'm going to leave it at that. So we essentially have, we can rewrite this whole entire expression. Remember your exponent rules. 2 to the power of n plus 1 is the same as 2 to the power of n times 2. So we're going to do the same thing here. But in this case, we're going to use log 2n. So we're going to have log 2 to the power of log 2n times 2 minus 1, right? And then what do we do when we're analyzing time complexity? We said we're going to ignore all constants and multiplicative constants. So a multiplicative constant here is this number 2. We're going to ignore that. We're left with 2 to the power of log 2 n. And if you look up your log rules, you're going to find that there's a rule that says if you have a base, right? If you take a base and you have a log of that same base with some number, this evaluates to what? To that number. This is one of your log rules. It says a to the power of log a b is equals to b. Go look it up and make sure you understand that. So with time complexity, you need to have you need to revise your mathematical fundamentals, right? So we end up with big O of n using this method, right? So we followed each step. The most important thing for you to grasp here is this entire approach, this entire analysis. We're looking at, for each value of I, how many times does the inner loop run, right? And then we're summing all those up. You see, we took 2 to the power of 0 plus 2 to the power of 1 plus 2 to the power of 2 up until 2 to the power of k, right? And then we saw that this evaluates to what? It evaluates to a geometric series, right? Which I have the formula here. I'm going to put the formula there. It evaluates to a geometric series, right? And then we did all these calculations. So that's one problem. It's this problem on the screen. Let's do a similar problem, right? A more complicated problem. Let me show it to you. So let's go to another page, another new page. I'll illustrate this. So this problem that you're seeing on screen right now is more complicated and more complex than the problem which we've done just now. So what we have here, looking at this, I'll put it over here. I'll put it over there. What we have here is we have 3 loops. Now, when you have 3 loops, I want you to think, let me actually write this down. I'm going to skip to when it's written down. So you have for I is equals to 1. You have this loop, and then you have another loop, then you have another loop. Okay. Here's how I want you to think about this approach, how you're going to approach this. This analysis that we're doing really works best if you have a structure like this, right? Where you have 2 loops, an outer loop and an inner loop. But you can treat this whole entire block as the outer loop. So you're going to have to work this one out, and then whatever big O you get there, let's say log of something, whatever big O you get there, you're going to multiply it with this big O of this line over here. Now let's tackle this problem. Let's start off with the first 2 outer loops, right? We're going to treat the first loop, this one, I'm referring to the first one on the problem. We're going to treat this as the outer loop, then we're going to treat this one as the inner loop. Then after we've worked the time complexity for this block, we're just going to multiply that with whatever is in here, right? Everyone is with me so far. Okay, let's do this. So first, we have our outer I is equals to, you can draw a little table, you're doing your counting over here, and then you have inner loop run. So each time we're asking ourselves, for every value of I, how many times does the inner loop run? So let's start analyzing this, right? So initially, what's the first value of I? We have I is equals to 1. Perfect. How many times does the inner loop run? Right? You see j starts at 0. And the condition for j is that j be less than I. So currently j is 0 and j is less than 1. So we're going to execute only once. Make sure you follow on that. And then what happens to the value of I? It multiplies by 2. So we have 2, right? How many times does the inner loop run when I is equals to 2? Twice. Because it's going to run for I is equals to 0. So j is first going to be 0 and it's going to be 1. Right? The last value is going to be 1 because we're less than 2. Right? So this will happen and you'll see this pattern. 4, 8, up until the last value. What's the last value? Judging from your condition, we have the termination condition I less than n, right? And I want to highlight again the largest value for I in this case. We can take that as n minus 1, right? The largest value for I. But remember, you have constants. That's going to be a difference in constants. What do we do with constants in the end? We're going to get rid of constants. So we can say that the last item, the worst case for this, the last item is going to be n. Not exactly n, but I is going to be as close to n as possible, right? That's what an upper bound is. Likewise, we're going to have something similar up until to some number. But you see a pattern here. We have 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, and so on, up until 2 to the power of k, right? And we have a similar outcome. We can see that the last, when we reach termination, right? When we reach this value of n, or the last value of I, rather, when we reach the last value of I, which you said has an upper bound of n, we're going to have how many iterations? 2 to the power of k iterations, right? So this is our Tn function. We're going to sum all these up, right? So for the first iteration, it ran only 2 to the power of 0. Second iteration, 2 to the power of 1. Third iteration, 2 to the power of 3, and so on up until the last iteration, right? Great. Which sums up to your geometric series. And if we substitute the value of 2 as a, we end up with 2 to the power of k plus 1 minus 1 over 2 minus 1. That's the geometric series. Geometric series, right? What happens after this? See, we have a problem. We don't know what the value of k is, right? But that's no problem because we have this expression over here. We said for the last value of I, which you said is going to be n, based on our formula, based on our termination condition. So you actually read your for loop and find out what's the largest value for I, right? You read that from the loop structure and then you simply write it here. You're saying, hey, the biggest value for I doesn't mean that I is going to be exactly that value, but the biggest value for I that I is going to get close to is n. And when that value is n, our iterations are 2 to the power of k. And then you check, you see that this value over here is going to be the same as the value under the table. Do you see that? That's equal to that. So for the last one as well, this is going to be true, right? So we simply have n is equals to 2 to the power of k. We take log of both sides, n equals to log 2k. We know our log rules, we can bring k to the front because it's an exponent of 2. So we have k log 2 is equals to log n, right? And then we're going to divide both sides by log 2. So this is going to cancel out. This will change its base to log 2 of n is equals to k, right? Then we simply substitute back the value of k. Simply substitute back the value of k. So we go back here. So we have the denominator here is going to evaluate to 1, so we can drop it out because it's 1. So we have 2 to the power of log 2n plus 1 minus 1, right? Then we said already the denominator is going to be equals to 1. So what do we have? We have 2 log 2n times 2 minus 1. And here's something that you need to be able to identify. This is one of your log rules, where we have a log a b is equals to b. So keep that in mind. So it's a good idea to go back to your log rules and make sure that you're able to spot these whenever they happen. It will save you a lot of time and headaches. So after this is going to be n times 2 minus 1, right? This is our T of n. So T of n is equals to n times 2 minus 1. What did we say we do when we're analyzing time complexity? We're ignoring all multiplicative constants. So we're ignoring 2. And then we're ignoring this minus 1, which is a constant. We're left with T of n is equals to n. Equals to n. Which means we have big O of n. We're not done yet. Right? We're not done yet. You have to keep in mind this was for the 2 loops combined. 2 outer. This is for the 2 outer loops. This is for the 2 outer loops combined. I hope you could see all the working out as I was writing this. Okay. So two outer loops combined give us big O of n. We're still left with that innermost loop, that for int k is equals to 0. Now we're focusing on that one. We know what the time complexity is for the 2 loops combined, the 2 outer loops. Now we're going to have to work out what's this innermost loop time complexity and multiply it by whatever time complexity we got for the 2 outer loops. So let's look at that. This one is pretty simple, right? So looking at the innermost. So looking at the innermost, right? We have T of n is equals to what? Now, this is a simple example. You can do primitive counting here. But when doing primitive counting, you have to keep in mind that you are going to come across constants, right? So in this approach, I'm going to ignore all the constants and then evaluate what's the number of iterations this loop is going to have. So we're starting from 0, right? We're looping until k. We're looping while k is less than n. So we're going to start from 0. Let's say n is 5. So we're going to start from 0, 1, 2, 3, 4. When n is 5, it's going to be 0, 1, 2, 3, 4. So n is equals to 5 and we're looping 5 times. So we can deduce that this innermost loop has time complexity of n. So that's straightforward. Which gives us big O of n, right? Now we have the innermost loop. We simply take this. Now we've simplified our thing. We simplified our expression. Right? So we're going to simply take big. So the total T of n is going to be equals to the outermost times the innermost. Right, let me label this. So this is going to be outermost then this is going to be your innermost loop. And then this simply means we have big O of n times n, right? And then we have big O of n squared. Now that you've understood this, here's your homework. I want you to go find problems in your tutorials or in the worksheet and then make sure you fully understand this approach. Right? Make sure you fully understand this approach. Let's close this video down by going back to the steps. So going back to the steps, what can we say? Here's the big picture goal, or the big picture mission that we're after. We can say steps, right? Steps. So we're going to evaluate we're going to evaluate what happens for each value of I out to loop. You're going to sum all those terms up, right? You're going to get your series, and then you're going to simplify, right? So thank you for following along this tutorial. I hope this alleviates all confusion that stems around time complexity analysis, right? Hopefully now you can get any algorithm and get its time complexity using this method. Now it's important to note that you must keep in mind of all your log rules, all your exponential rules, as they will come in handy, like you've seen for this particular problem. All right, that's it for this video. You can click like, subscribe if you love it, if you found value in it, and then do your homework. All right, see you in the next one.